All right. So let me try to demonstrate where these matrices are used. Matrices are used in many different places. You're going to see them in many contexts. But the simplest place where you can use matrices is when you solve system of equations. So let's say you're trying to solve 2x plus 5y equals to 3 and negative 3x plus 2y is equal to 5. What we want to do is, I want to change this into a matrix form, and using this formula for inverse of a matrix to solve this system. Okay. So the first step is to change this into matrix form, and always follows the following format. What you do is first write down a matrix which is called the matrix of coefficients. Okay, so you look at the coefficients 2, 5, negative 3, and 2. You record it as a matrix 2, 5, negative 3, and 2. And when you do this, you have to make sure that the matrices, the variables are in the same order. You can't write down 2y minus 3x, then these two will be all messed up. So make sure that you're following some order, usually alphabetic order. So you write it like this. And then you write on the next, right next to it, something called the matrix of unknowns, which are the unknown variables, x, y. And you set it equal to the numbers on the right. So in the case when you have ax plus by equals to a number, cx plus dy equal to another number, you can always represent this system of equations in this format. Now let's check why this is equivalent to that. To see that, you should actually do the multiplications across down, right? So what's that? 2x times 5y, right? So it's 2x plus 5y. And if you multiply across down, negative 3x plus 2y. And it's a single matrix, right? It's a 2-by-1 matrix. And we're trying to say that this matrix should equal to 3, 5. What does that mean? That means each element should be equal. So 2x plus 5y is equal to 3. Negative 3x plus 2y is equal to 5, which is exactly this equation, right? So now you see that this is just a representation of this system of equations in a matrix form. Okay. All right. Now what do you do? Well, look at this and see how it looks like. If I call this matrix as X, and if I call this matrix as A and that as B, this system has the following form. It's AX equal to B between matrices. So it's a matrix times a matrix equal to another matrix. Now, let's forget for a moment that these are matrices and think about a corresponding equation. How would we solve this one? If I just had ax equal to b, how would we solve this? Just divide by a, right? That would be the answer, right? Now, coming back to this context, how would we solve this one? You would multiply by the inverse. Okay, so this can be done as a inverse times b, right? In the same way, what we're going to do is I'm just going to solve this by multiplying by the inverse of this matrix A, and immediately I get what x is. Right? Now, there's one thing that you have to be very careful. I didn't show you by example, but if you multiply two matrices, the orders do matter. So, warning. It is not true that AB is BA. This is not true. So in general, in most cases, A times B is not equal to B. In most cases. So if you write two 2x2 matrices and you compute AB and BA, in most cases they will be different. Of course, there are some cases they do hold, which is like when B is the identity. It's true that AI is equal to IA, and it's equal to, in both cases, it's same. So in very few cases, they do commute, but in most cases, commutativity is not true. In fact, there's a whole theory about when matrices commute. And that's actually a hard question, trying to ask what conditions should matrices satisfy in order for them to commute. It's a hard question. Okay? So just know this, right? So when we solve this by multiplying by A inverse, it's very important that you multiply it to the left side. You should never write it as B inverse. Actually, in our context, it's actually impossible to multiply the inverse of this to the right. Because this is a 2x1 matrix, you can't multiply to a 2x2 matrix. It's impossible. So you know that it has to be multiplied on the left. Okay? So already that tells us that I should be doing this. Okay? All right, so I know that the answer must be A inverse of B. So let's calculate it. We know that xy must be the inverse of 2, 5, negative 3, and 2 inverse times the two numbers 3 and 5. And for this one, we will be using this formula. Okay. So let's try to memorize this. What does it do to the original one? If you look closely what's happened, you see that the diagonal has been interchanged. So you switch the diagonal, and these two off-diagonal elements are negated. Okay? And then you divide it by AD minus BC. Okay? Got that? So that's exactly what we're going to do. We're going to switch these two. Well, it's not interesting because they're the same thing. 2, 2. And then we're going to negate these two, which is negative 5, positive 3. And then we're going to do 1 over AD minus BC. I usually do it like this, like a fish shape. So it's AD, which is 4, minus BC, which is 5 times negative 3. So 15 and 4, that's 19. Times 3, 5. So I know that's 1 over 19. This is 1 over 19. And then I have to multiply these. So let's see. 2 times 3 is 6. Negative 5 times 5 is negative 25, so negative 19. 3 times 3 is 9. 2 times 5 is 10. 10 plus 9 is positive 19. So when you divide, you end up with negative 1 and 1.
Where'd you get the 4?
4? Oh, it's AD minus BC.
Okay.
So 2 times 2 minus 5 times negative 3. All right, so it's telling me that negative 1 and 1 are the answers. Let's see if it's true. If x is negative 1 and y is 1, is it true that you get 3? 2 times negative 1 plus 5 times 1 is 3. And negative 1, 1. Negative 3 times negative 1 is positive 3. 2 times 1 is 2. And it does add up to 5. So you do see that the answer comes out to be negative 1, 1. Yes?
Can you go through that several more times, please?
Which step?
How you got 1 over 19 and negative 19, 19.
Okay, so this much is the inverse of this matrix using this, okay? And after that, so another thing is that matrix multiplication is associative, meaning that as long as you don't change the places, you can compute in any order. Okay? Even when you have a scalar with matrices, it's associative. So rather than dividing this 1 over 19 to each element and then multiplying, it's better to just compute this one and then divide. Okay?
Yeah.
So I'm using the associativity. And that makes this calculation much more convenient. Okay? And then if you now multiply these two matrices by doing across down, I get negative 19 on top. Across down, I get positive 19 on the bottom. And I still have 1 over 19 coming from here. And then when you divide both of them by 19, I get negative 1 and 1.
Okay.
Yeah.
Thank you.
Any other questions? So that's how you solve a matrix using solve a system using matrices.